Hi, I'm Charles, and welcome to part 27 of the OpenSCAD video series. In this part, we're going to be talking about the sweep technique and two different ways to implement it. So let's get started. So the first thing that we're going to need to talk about a little bit is vectors and vector addition and subtraction, because that's going to be an important technique that we are using here. So as you can see here, we've got some things that represent vectors. I'm going to scroll down a little bit. This is just a demo. This isn't the relevant coding portion of the video. I'll be uploading the demo as well, so you can see it if you like. So the important thing here is this part right now. So we've got, in this image here, we've got three vectors. We have P1, which is this red vector right here. We have P2, which is this blue vector right here. So you can see that it's 0 in the x, 0 in the y, 10 in the z. And this is 10 in the x right there, 0 in the y, and 15 in the z. So we can essentially add and subtract these vectors. The operations of vectors are defined with addition and subtraction and other things. So if we listed it down here, what it would look like, essentially you add or subtract each element in the vector. So if we're adding P1 and P2, we can do that here like this. We get P3, and we'd essentially be adding 0 to 10, 0 to 0, and 10 to 15. So if we look here at the addition, because I get it to print out here, we get 0.3, which is P1 plus P2, is 10, 0, and 25, which is 0 plus 10, 0 plus 0, and 10 plus 15 is 25. So that is correct. So, and P4 is P2 minus P1, so this is a similar operation. We subtract P1 from P2, we take 10 minus 0, 0 minus 0, and 15 minus 10, and it leaves us with 10, 0, and 15. And actually, the P4 vector is our green vector, P2 minus P1, as it says here. And why we do that is important. So essentially what we want is, let's say we have some point in space represented by P1 over here. That's our first spot, and this is our second spot, P2, and we want some vector that, when you put the tip on it here, points to P2, from P1 to P2. Now, it could be from P2 to P1, it could be from any vector to any other vector, but in this case, we want it to point from P1 to P2. Essentially what we do is we take P2 minus P1, and that gives us a vector pointing from P1 to P2. Now, actually, the vector that you get is this one at the bottom here, starting at the origin, pointing over this way. But when you add height to the base of it, like if you add P1 to the base of it, that's technically not an operation. You're kind of just putting a vector in a particular spot. You end up with P2. So if you, this kind of shows how you get there. So if you have P1, P2 minus P1, which is this green vector, and then you add P1 back to it, you get P2. Or if you start with P1, and then you add P2 minus P1 to P1, then you end up with P2, which is what we're going for. So this vector, the important thing is that this vector points from P1 to P2. And so we could change that. I can show that. let's say I make this, I can make this 5, I can make this 20, and that gives us a different vector, but it gives us the same thing. We have this, this P, maybe this could be a little bit more interesting. Yeah, so if P1 is pointing in this direction, P2 is pointing over here, and we want this vector, this green vector, to point from P1 to P2, we can do that. We just say P2 minus P1, and that's this green vector. So that's that. So the sweep operation, we're going to kind of talk about what it is and why we need it. Maybe I should have mentioned that first, but this was the first thing, so I wanted to get to this first. So what I have here is just a group of points. So I've created a list comprehension. It is up here, these points. With these functions, I just created this list comprehension and made a bunch of points. So, and I'm just displaying them here. So let's say we wanted to connect all these points. We have all these points. We have some sort of path or like some group of points, and we want to connect them kind of sequentially, and not just like as a big lump. Because let's say if I just connected all of them together with a hull, we'd end up with probably something close to a cylinder. Yeah, so not quite a cylinder, but definitely not a sequential connecting of the points. So let's change that back. Yeah, so we want essentially a line going through them. Now one way we could do that is with a chained hull. So this is what that would look like if the cubes were a bit bigger and we just chained hull them all together. Code for that is down here. We just connect one cube to the next cube, but we sort of get, it's not a very elegant shape, I would say. It might be functional, depending on what it is you need to do. This is one option, but I would argue not the best option. So, let's see. So, as you can see, like this part here is flat, but if you go over here, this part is flat, but it's more of a diamond shape. And like this part is not flat, it's got this kind of wonky shape. So you get this sort of maybe artifacts, these strange shapes. So this is not the best method to do this. So this should show the first technique that we want to do. So here, essentially what we can do is we can take shapes and point them in the direction that we're going. So we can essentially take a starting point and then point it at the next point. And if we do this and we continue around like that, we will get something that better resembles a pipe or like a cylinder swept along a path, which is ultimately what we're going for. So this is the first technique, and this just essentially what this does is it points the arrow or the object from the starting point over here to the end point over here. It just points it to the next point. There is another technique which is slightly different, and you could argue it's slightly better. That there's a bit of a gap here because of the way the technique works. That can be fixed in a lot of cases. it doesn't quite point from, let's see, maybe this is a better example. This area here. It doesn't quite point from the previous point to the next point. It kind of takes, what it actually does is takes 2 points on either side of the starting point and finds a vector between those instead and points in that direction. So yeah, those are the 2 techniques we'll be looking at. Let's see. And so this is the first one. This is the original sweep technique. And as you can see, this, like, it's okay. There, you do have a bit of an issue here where, like, the things overlap. There's not much you can do about that without changing the size or your like the size of the cylinder that you're sweeping or the shape of your path. So yeah, that's the first technique, and this is the second technique, and they look not too different, and in a lot of cases they aren't too different. Essentially, if you make the number of steps bigger, like the number of cylinders that you use as you sweep it around, the better your results are going to be in general. But the second technique might just help you a little bit if you're using fewer steps. It may or may not. It depends. Okay, and here is more of an explanation of the points. So let's say we have this group of points. It's just duplicated twice. They're the same. This first point, second point, third point, fourth point, fifth point, and we want to sweep a cylinder along this path. How do we do that? Let's look at the first technique. So from any given point, let's say we pick this point, we take this, like this direction, the red one represents the direction, and we just create it. So if we imagine these 2 points as vectors, we take the second point minus the first point, and we get this directional vector, which points from this point to that point, and then we just aim our arrow in that direction, essentially. In the second technique, we have this point that we're interested in. We want to figure out the direction for it to point in, but instead of taking this point and this point, we take the 2 points around it. So it'd be this point and this point, as we can see here, that one and that one, and we find a vector between these. And this is now our direction vector, and this is the direction we pointed. And you can see that in the first one, this is pointed directly to the next point, and in this one, this is not pointed directly to the next point. It's pointed a little bit off, but that is the direction of the surrounding points. So that is that. I think that is all of the explanation. So let's get to it. So we're gonna borrow some things from previous videos. So this pointing function from the pointing videos. Here we're gonna take that, and so this points an object from going straight up to wherever we want it to point. So just to give a quick example, point to, let's say, So we have this cylinder. If I get rid of this, it's just straight up, pointing straight up. Maybe 1 or 2. So yeah, kind of a cone shape here. And let's say we want it to point to this point. So let's say we want it to point to this point over here. How do we do that? Well, we use the point2 function. That's covered in a previous video. We're just gonna use the function. So yeah, now it's pointing at. And if we extend this a little bit, we can see what it is. Yeah, there we go. So now it's pointing directly at the cube here, and this is part of the technique, or this is part of the technique, and we're going to use this function, the point2 function. So don't need this. So the next thing we're going to steal is from the list comprehensions video. I just want to take the not making. Whoops. Just going to take the not making function and add that in so that we have some points to work with. So these are going to be our points that we're working with. So I believe start 2, 3, and let's go for 300. And now you can't see anything, so we're just gonna show them. There we go. So here is our trefoil knot. And we want to sweep a cylinder along this whole path so it becomes like one big like tube or bar or whatever that's connected by this. So here are the points. Yep. And now we're going to work on the sweeping functionality. So this is going to be a for loop. So we're going to need to make an iterator. Not an iterator in common sense. We're just gonna go from 0 to I'm going to take the length of values. I believe it is -1. It might be, there might be another one. It gets a little funky here with the ending conditions. So if it's a loop versus if it's just a thing that isn't a loop. For example, if I made this for 2, right? So this is no longer a loop. This has like a start and an end, and And if it has a start and an end, it works slightly differently than if it's a loop. So just something to keep in mind, because you end up losing, you might end up losing some points if you're not careful, but it's not too tricky to figure out. So in this case, yeah, generally we want to do -1. So we essentially need 3 points. So we say P0 is P0 is the point in question, so we'll say values I. Then we need the next point. Values I plus 1, and then P2. I plus 2. So it might not be immediately obvious why we need 3 points as opposed to just 2. But it's because we're going to be using the chained Hall method. And the chained Hall method requires, well, at least in this case, we need to know the position and the orientation of the first object that we're sweeping, or the object that we're sweeping at the first point, P0, but we also need to know that position at P1 as well. So that's why we need 3 points. So, sorry, let me just change this back. Okay, so essentially what we're going to do, we need a vector that points from P0 to P1. So to get that, if you remember in our demo, if we go back here, we know that if we want a vector to point from P1 to P2, we need to subtract P1 from P2. So in our case here, we want the vector to point from P0 to P1, so we subtract P0 from P1. So we get direction is equal to P1 minus P0. And we're going to need the same thing. We need P2 direction 2 is equal to P2 minus P1. So what we actually might want to do is direction 1 and direction 0, so that we know that this is the direction when at P0, the object at P0, and this is the direction of the object at P1. So let's do that. So we're going to use this function, the point2 function, point2 location. So let's say direction 1, or direction 0, sorry. So let's have a cylinder. That makes it simple. R equals 0.5 equals, now we want them to be generally pretty thin, so 0.001, it could be 0.01, 001 is pretty small, and will generally, it makes it seem closer to a smooth shape. The center should be true in this case, and we can change the number of values, but just to keep it simple, maybe we'll pick 30. So if we do all this, it did not like that for some reason. Let me just see what's going on here. I think I know. Yeah, this is probably what the error was. So I was going I+2, and I was probably going past the number of values that there are. So if I do it again, no, it generated one warning, so I need to subtract 3. Okay. So this ball does not look useful at all to us, and actually this is a bit big. So now we have the smaller ball. With the smaller ball, this is all our cylinders kind of pointed in the different directions. And it's kind of an interesting looking shape, but not what we're going for here. So what we need to do is move this to where it's supposed to be. So let's move this to P0, because this is the direction, like these are all the directions that should be utilized at their specific spots. So let's say P0. And now we can see. Let me just comment this out. And as we can see, we have all these things pointing in the direction. Maybe the height's a bit small to like properly visualize it. Nope, that's too big. There, that's a bit better. Okay, so we can see that we have this gap here, which is the problem, but first let's look at the things. We can see that they're all kind of aligned along the path, all perpendicular to the path, which is good, or parallel to the path. Their kind of central axis is parallel, and then the rest of them is perpendicular. So that's kind of what we're going for, so that we can join them all together. So we have this gap here, and this gap in this case can be fixed because it's a loop. In this case, because it's a loop, it can be fixed by moduloing with the length of values. So it wraps around. Except that does not work in this case, so there. Okay, so now we have them, no errors, and we have a complete group. So that's good. But okay, so that's good. We have one of them, but then we need the next one so that we can do the chained hull. So we need to use our second direction, direction 1. So point 2, direction 1. And actually we want our cylinder to be exactly the same. So I'm just going to copy and paste that. And voila, it looks like nothing has changed, which is good, actually. So, oh no, never mind. Something has changed. We have another ball in the middle. So again, we have to translate them to where they need to be, and they're gone. And now this looks like nothing has changed, more or less. But if we do this, and that, we can see that we now have 2 different cylinders on each spot. And now if we hull them together, we can see what we get. And so we can see that when we haul them together, we get a sort of cone shape from the small one, which is first, to the big one, which is second, which is exactly what we want. So now if we just change these to be the same size, we get our swept shape, which has a bunch of different uses, which is pretty cool. Yeah, you can also do this with a square. So if we take this down to 4, it becomes more like a square. And yeah, you can sweep a square as well. This doesn't work with shapes like a star because it has like some concave points, and those would get filled in by the hull. But any convex shape any convex like 2D shape should work. So yeah. So like if you could extrude something from the 2D subsystem, and then have it be swept along here. You can't do it directly from the 2D subsystem. You need to turn it into a 3D object first, and then you can sweep it along the path. Okay, so that is the first technique, and it's decent. So now we're gonna do something pretty similar for the second one. So we'll create another for loop. Maybe I will just this is taking too long. Type equals 0. So we'll just say this is type 0. So this is the first one we do, and that gives us this one. And if type equals 1, we do the next one. So again, we make another for loop. I is equal to 0 through when values -1. So this one is a little bit trickier just on the indexing, but we're actually going to need 4 points. And why that is, so if we go back here, go to 6, yeah, if we go to this one, so this was the first technique that we just did. This is the second technique. We need, for this one, for each point that we need a direction for, we need 2 points. So for this point, we need this one and this one. But for this point, which is going to be here, we need this point and this point. And for any given section, we need two objects to put together. So we need 2 points for each part of the object. So 2 here, and then another one here, 2 here. Yep, that's it. So we'll go back to it. So call this one P-1, because it is not P0. It's before it. So we'll say this is values, and then we're gonna have to index in an interesting way. I'll come back to that in a sec. P0 is equal to values I. P1 is equal to values I plus 1, and we don't want to forget the modulo. Modulo and values. So it wraps around, and P2 is values, I plus 2, modulo len values. Yeah, and so this one is I minus 1 plus length of values, I believe. Hopefully this is right. And then again moduloed by length values. We'll see. Hopefully that is correct. Just because, actually I learned that OpenSCAD, I don't think you can index a list with negative numbers. So you need to do this sort of wraparound where you essentially get the negative indices. Yeah. So, yep, that should do it. Okay, so now, let me change this to type 1. And we get nothing because we're just running this. So, remember we need, for the direction for P0, we need to point from PM1 to P1. So we'll say direction 0 is equal to P1 minus P minus 1. And that gives us our first direction. So we'll do a point 2, direction 0. We'll do a similar thing, cylinder. R equals 0.1. Maybe I should just copy and paste this. Yeah. And make it a bit bigger so it's a bit more interesting. And then we get our ball in the middle because we have all these vectors that are pointing in the direction, but we haven't moved them to where they're supposed to be. So we'll just move them to where they're supposed to be, which is P0. And there we go. So that's good. So now we need the next one. Sorry, I wanted to maybe just show what happens if we don't have, if we just pointed these things in the same direction and we didn't, change it. So if we have both of them pointing in the same direction, get these subtle artifacts, kind of hard to see. And like, you know, this might even work because the artifacts are so small, but you can see that they've got these edges that are not quite right, and it should perhaps be even more pronounced. If I took this down a step, yeah, you can start to see, or several steps, you can start to see these edges that aren't lining up properly. But that is corrected when we have them pointing in the right direction. So this cube here, it's kind of hard to see if I take away the hull. There we go. So we have two that are overlapping. They've been moved to the same point. But one is pointing in the direction it's supposed to be pointing in. I believe this one's in the right direction. The one on the right is in the right direction. And the one on the left is pointing in the same direction as this one, the one from the left. And they don't line up. So when we do the section on the left, we need to make sure that the point here, or the object here and the object here, are pointing in the direction they should be for that point. So for these two objects should be pointing in the same direction, and that's why we have the two. We need both directions for each segment that we make. And so when we make that correction, they all line up together. And we get our shape, which is good. So we move back to focusing on this one. So we need our second direction to be able to do anything. We have these, which is good, but we need our second direction. So direction 1, so the direction for point 1 is P2 minus P0. So we're skipping over P1 when we're calculating the direction that they need to point at P1. So we say point 2 minus P0, and then at point 0 we were skipping over point 0, so we do point 1 minus point minus 1. And that gives us the directions that we need. So now we have both directions. Let's do what we need to do with them. Direction 1. So we got a little ball in the middle, as we've been getting a bunch of times. Again, they're not moved to where they need to be, so we need to move them to where they need to be. P1. And so we can't see the difference. It looks pretty much the same, but we're not seeing them being rotated a different amount. So all the objects which are at the same point are rotated the same amount, which is good, which is what we want. And now we can haul them together. Sorry, if I change this up, we can see. Nope, what am I doing? So that's 2. There we go. So yeah, we can see. Yeah, now we can see that there's 2 different cylinders at the same spot. I'm just trying to make it look good, so you can really see. Okay, so we've got the 2 different cylinders at the same spot, just like we did in the last one, and we can haul them together. And we get a similar looking shape to what we did in the last one. So now we just have to make them essentially the same size. And boom, there you go. That is the sweep. So let's really try and take this down, because it's the difference between them is less noticeable when you have more steps. They pretty much become the same. So let's see. So that is with 50 steps. That is the improved version. That's type 1. This is type 0. Sorry, they need to be the same to actually make sense. So they are the same except for that. So let's change this back to type 1. So this is the better one. That's the one we just did. And this is type 0. So a very subtle difference, hard to see. But arguably the second type is a bit better. Maybe if I bring it down even further. I don't know, if I bring it down too much, it doesn't really make a difference. It's all just bad. Yeah, kind of hard to tell. but they both work. Whichever is easier, works better for you. Yeah, I mean, the first version uses fewer points that you need to calculate, and you would lose fewer points at the end of a stretch, so that could be a plus factor. I wanted to show something else cool that you can do with this. So let's take this back up to 30. So now we have our kind of pipe structure. So if we take this now, what we can actually do is change the size of things as we move around. So we can make an iterator essentially. So we can say I is equal to I over len values minus 1. And we can so we need actually 2 of these for the chained haul. So now we can change the size of things. So if we made the radius dependent on where we were in the curve, so let's say the radius is equal to 0.1 plus 0.05 times sine of 360, maybe like 4 times 360 times I. That'll give us something kind of interesting, although it's kind of hard to see. So we need to actually put it into the next one. So if we do that, we just need to make sure that it's I2 because it's the second one. We're not dealing with what's at point 0, we're dealing with what's at point 1, so they need to be adjusted accordingly. So yeah, we get this sort of interesting shape. Maybe if I make this a bit bigger, I can make the effect more pronounced. There, yeah, we get this kind of like strange undulating effect. And we can change how many times this happens just because of the way this is. And you can put any function in here that changes with the position kind of along your points. If I change this to 6, yeah, you get this sort of interesting shape, which is super weird and organic. And I have a problem here. I've sort of goofed. What have I done? So this is a bit of an issue. This just might be an off by 1 error if I do. Nope, that makes it worse. There we go. If you just divide by length values as opposed to length values minus 1, that fixes this in this case. Might be a bit different if you don't have a full loop, but here we've got a full loop. So yeah, that's an interesting shape, and I guess maybe I'll add some color to it. Maybe 0.5 times sine, no, plus 2 times sine of 360 times I. Do something similar. The next one. No, this should work actually, and we'll actually give it some transparency. Okay, so hopefully this works. I don't know what these colors are gonna look like. Oh, there you go. Interesting. Maybe we should change them just a little bit more. And then maybe make them a bit more vibrant. Yeah, that's kind of interesting, but okay, so let's take this. Making the colors is always an interesting part. Is it happy about that? I don't know if it's happy about that. Getting any errors? Nope. Oh, maybe it is, but it shouldn't actually be happy about this. This is not changing the colors at all. I'm very confused. Okay, so let's change this up to just kind of look really nice. Maybe bring this to like 12. $300. Yep, that looks kind of cool. And that is the sweep method. So yeah, you can use different functions for this. This is just one of the functions that you can use, and you can do some interesting things with this. So yeah, thank you for watching, and hopefully I'll see you